Thanks for the introduction. I'll just get right into it, save a little bit of time. I get a message. All right, there we go. Okay, so the problem I'm working with here is that complex data that has shape and dynamics. What I want to be able to do is analyze that data. And the question is, how can I do that? So this animation here kind of shows the complexity of what dynamic social network can have in it. But also you see this complex data in cyber as well as other forms. And what we want to know, so we can try to measure the shape of it using topology, but generally this requires that we're only looking at a static point of time of this. So like I could take over the entire time domain, I could take the whole graph and look at its shape, but that doesn't really tell me how the dynamics are involved and how is it evolving time. So to do that, I could use maybe tools from dynamical systems where I could take maybe a time series from this and then do some analysis on this to understand at what time scales is this data evolving. Well, I really want to be able to do both. So to do that, I'm going to use what's known as zigzag persistence from the field of topological data analysis, which then combines both dynamics with topology to understand how is this underlying system evolving. So as an outline of this talk, I'm going to start with an introduction of what is topology, and then what is topological data analysis, or how can we apply topology to data. And then I'll talk about hypergraphs and temporal hypergraphs, and then how we can study them using zigzag persistence. And then lastly, I'll go over a couple examples with two data sets. So let's start with what is topology. Topology, we can think of it as just the underlying shape of a structure, not the size of it, but its shape. So here on the right, you can see that we have both a coffee cup and a donut, but they are topologically equivalent since they only have one hole in them. So to introduce it a little bit more lightly, we can kind of categorize these as Betty numbers. So it's just a sequence of numbers that describe how many n-dimensional holes there are. So Betty 0 are the zero-dimensional holes, which are components. So it's the number of components. Betty 1, number of holes. Betty 2, number of voids, and higher dimensional holes from there. So some examples are from left to right, you have just a point, which is just a Betty 0 of 1. Everything else is 0 because it's just a single component. We have then next to that a circle, which has a Betty 0 of 1, and because it's one component again, and a Betty 1 of 1, since there's that one hole there. And then there's no void, so it's a Betty 2 of 0. And then next, Betty 0 of 1. There's actually no hole in a sphere, right? It's just hollow, so that Betty 1 is also 0. But there is now a Betty 2 of 1 because it's hollow. And last, we have the torus, which has, it can be a little bit confusing to see, but it has two holes, one base that can't collapse. So one around the through the middle, and then also inside of the torus, and then also one void because it's a hollow torus. So now that we have an understanding of what topology is and what I'm talking about that, how can I apply this to data? Well, to apply this to data, we need to get it into a simplicial complex, and you can do this through sub or super level sets. You can also do it through point cloud data, as well as graph data or hypergraph. There's really a ton of ways you can go from data to a simplicial complex. So one of the more common ways is, well, first we need to get it to an abstract simplicial complex so we can study its shape using those tools from topology, so those Betty numbers, right? So let's look at a few example simplicial complex. And what I'm talking about with an abstract simplicial complex is a collection of simplices where that is just a set of points. So for example, you could have a face with 3 points as, let's say, 1, 2, 3, and then it's also closed with a smaller sub-simplices, so you then have to have all 3 of those edges as well as the vertices there. So here you have these 3 different simplices, and we can again measure their homology using Betty numbers, where A has one hole and it's one component, and that's filled in, and then B, that's a hollow shape there, so we have Betty 2, and then the C, we have 2 components, so Betty 0 is 2, everything else is 0. So now that we know what algebraic topology is and how we can apply that to abstract simplicial complexes, which can be represented from data, let's see how we actually apply this to a standard approach for studying data using topology. Now, this is known as persistent homology. So here, what we want to measure is the shape of this data. So we have some points known as a point cloud. They're generally a circular shape with a hole, and we want to be able to measure that. To do that, what we're going to do is construct the Vietoris-Rips complex, where we draw spheres around each of these points of a certain radius r, and then as those points are, whenever those spheres overlap, we can create simplicial complex or simplices from those. So here's now the drawn simplicial complex, where again, now we're able to see that there's a hole there, measure it with topology with a Betti-1 of 1. But that doesn't tell us anything about really the geometry, the size of this hole, and in that choice of the radius of those spheres is not trivial. And so the question is, how do you choose that? And the answer from persistent homology is you don't choose, you choose them all. And what we do instead is we do a filtration as we increase the radius of those spheres and then look at the homology or the Betti numbers at each of those. So the bottom right, the H0 and the H1 are known as barcodes, which track when do topological features appear and then when do they disappear. So we can see all these components as these red bars moving across. And then about right now, that circle form shows up in H1, and it keeps persisting for a while. So eventually it fills in. And then so now we can see that there's the significance of that circular shape through those barcodes, which is important. So now we're getting more than just the topology of it. We're also getting a little bit of an understanding of the geometry of this data. Another quick result is that there's a stability here that if those points were shifted slightly, you'd still get a very similar persistence barcodes, which then makes this very useful for applying to real data. Yeah.
So you say stability results, so there is a proof that this actually is the case?
Yeah, yep, there is. It depends on the data type, of course. Here with point cloud data, it is the stability result is true. So it will, those barcodes will only change proportionate to how much you move the points. It is not resistance outlier, but there are variations of persistent homology that is resistant. It's just how you do this filtration really, and how you represent the data as a simplicial complex that matters there. So now we've gone over this, this general sequence, right, where each simplicial complex, as it increased this radius r, was a subset of its previous, right? So this is not always the case, especially in these temporal dynamics, right? These complex networks that we're working with, where maybe some of these edges or hyper edges disappear over time, and then they come back. And how are we going to work with that? Because this framework required that each simplicial complex in the sequence was a subset. So to do that, let's say we have this case where we have some homomorphism between the simplicial complexes, but not in both directions. So that's kind of still a problem. So let's go to the most arbitrary case where we just have a sequence of simplicial complexes. We don't have any relation between them. But what we can do is we can force a relation between them using, this is how zigzag persistence gets its name, either unions or intersections, so that our homeomorphisms go right and then left and then right and then left, zigzagging through the simplicial complexes. So in this work, we're going to mostly focus on unions, but then what we can do is a new filtration, which moves forward. You can kind of think forward in time, and then we can track how topological features persist through time instead of through space as we increase the radius r. So yes, this is known as zigzag persistence, and we'll get the same output where we get a barcode just like before, but now we're measuring when in time do these topological features appear and disappear. So to make this a little bit easier, we're going to just do a quick toy example. So here, K0, K1 through K4, those are our simplicial complexes that we had. And above that, K0, comma 1 through K3, comma 4 are the unions of those simplicial complexes. And then we have timestamps associated to each of these, right? So time 0, time 1, and then the unions, we just take the average of those two times. And what we're going to try to do is detect the components and the holes and how they persist over this sequence. So one of the things we want to look for in H1 or our Betti ones is that there's a hole here, and we want to be able to detect that. We also want to look at the number of components that there are over time. So we run our zigzag persistence, and we get these barcodes. And what we can notice is that in H0, we start with 2 components, representing these 2 bars, and then they persist until time 0.5, where the shorter of the 2 dies. These are half-open intervals, so they're open on the right side, so it does not exist at time 0.5. But the other component does persist over time, and that component keeps persisting. And then at time 2, we have this hole that's being picked up through the H1 here, which shows up at time 2, persists through time 2.5, through the simplicial complex, and then disappears at time 3. And then after that, that one component continues until again at K4, we have our simplicial complex splits, and we go back to 2 components. So what we can see is that, and then at the very end, we just make it an empty abstract ASC so that we can just kill all the barcodes. They all die at the end. But you can see that now these barcodes capture the changing topology of the sequence of abstract simplicial complexes. So next, how can we actually apply this tool from real data that we're working with? And specifically, the data that we're going to try to create these from is from hypergraphs. So I don't really need to introduce this since everyone's seen this probably at least 2 times so far today. Hypergraph is just, compared to a graph, it's hyperedges can relate multiple nodes together or connect multiple vertices together. So it captures multi-way relationships. Now, one way that we need, so now we need to go from this hypergraph though to simplicial complexes. And how do we do that? Well, there's a bunch of different natural representations of a hypergraph, which Cliff went over earlier today. We can treat them as a multi-set system where you have indexed sets, right? So AD, ACD, these are your hyperedges. We can also treat these as an incidence matrix where your columns are your hyperedges. So column 1 has AD, so that is a hyperedge. We can do Euler diagrams, which are the common representation. We can also do bipartite graphs. We're not really using any of these in this work, but what we're using is the simplicial diagram. Well, instead of the simplicial diagram, we're actually using the associated simplicial complex without all the extra information that the simplicial diagram has. So it's just the underlying simplicial complex of the simplicial diagram. So each hypergraph can be represented now as a simplicial complex. So let's see how we can apply this to temporal hypergraphs. So a temporal hypergraph is where every edge or node, but in this case, we're working with just temporal information on the edges, is active during a certain amount of time. So the plot on the bottom shows the intervals in which these hyperedges are active. And then we do a sliding window procedure where we capture hypergraph snapshots during each window for when these hyperedges are active. And now what we're going to do is take these 4 hypergraphs. Well, I guess, yeah, good. What we can do if we wanted to kind of naively approach this is we could just do summary statistics on each of these hypergraph snapshots individually and look at how those change. But that doesn't capture what zigzag captures, where it captures the connectivity or how the actual hypergraph is evolving. So we have these 5 hypergraphs, and we can get their associated simplicial complexes. And then we can take unions or intersections. In this work, again, we're doing unions. And we can get our zigzag persistence barcode. So this is exactly the same example as before, so I'm not going to go over the barcode again, but it's capturing that whole from K2 to K3. So now I'm going to go over some examples in data. So the first example I have is for Reddit data. So this is data from Social Network Problem Shop in 2022. I know some of you went to this. So this data is Reddit data collected with coronavirus-related, COVID-19 related subreddits. So you can see all the subreddits listed there. For this example, I'm just going to do the NCOV subreddit because it's one of the smaller ones, which makes visualization and understanding a little bit easier. This data was collected for almost a year during 2020, And this specific subreddit had 4,000 threads and 2,000 authors. So how we created these hypergraphs from this data was we treated each thread in the Reddit data as a hyperedge, and then the users in that thread as the nodes of that hyperedge. So here I show an example hypergraph from this data during this time. I also show here the edge index, where all those black lines there, those are the intervals when these hyperedges are active. So that's where our temporal information is. And I also below that show the number of edges and the number of vertices in each of these hypergraph snapshots. But again, this doesn't tell us how is this temporal hypergraph evolving through this time. So to answer that question, I'm going to use zigzag persistence. And what you can see, there's a few things I want to point out here. So on the top, we can see that these barcodes and H0, which again are the connected components and how those persist through time. There's one long one from about the first day to the 7th day. So it's not the whole time range of the data, just the first couple months of the data. But you can see that it persists the whole time. So that kind of signifies that there was a conversation in this temporal hypergraph that persisted over the whole duration of this subreddit. Additionally, we see that there's a bunch of these really short bars in the barcode that are representative of these very short-lived conversations. So there's a thread in this subreddit, maybe one person or two people posted in it, but maybe only went on for a couple hours or a day or something like that. Also, later on around day 27, we have this other component that persisted for a long time. So later, we can see that this kind of captures how the topology of this is evolving, these components. We can also see that there are a number of H1 with this snapshot hypergraph here showing that there is a hole in that hypergraph that's captured there. And that really signifies that this communication is, not everyone is involved in this communication, right? There's groups of people that are not communicating together, but they're all connected in the same hypergraph. And one thing we've noticed, while the interpretability of this is difficult, especially the higher dimensional homology, one of the things we've noticed is, and we're not sure if it's an artifact of the data, but when these hypergraphs get larger, we find that there are more H1s. And that might just be because the natural structure of this data being from a social network or not, but this is the trend that we've found. We also did this for unions versus intersections to show that there really isn't much difference in the barcode, so that choice doesn't significantly change the results. So that concludes the Reddit data. The next data set is the operational transparent cyber data, OpTC data. And what this data comes in is as a large table where we have timestamps for every line in cyber data that's occurring. So it was this study where they had 615 hosts, went over for a week, and they did benign cyber activity versus then they had some days where they had evaluation data where they had a red team that was doing some malicious activity. The goal of this data is to try to detect that malicious activity in the cyber data. And it's a really huge data set. So this is 10 terabytes of data. And this isn't even all the rows shown in the COM data. There's 58 rows. So it's really hard to understand this data, and it's very complex data. So to study this data, though, what we're going to do is we take the full log data, we break it into windows. So here are 10-minute windows. And then from each of these windows, we're going to get a hypergraph representation of that data. In the specific hypergraph representation, what we do is we first filter down by a source IP, so that this way we can get a resulting barcode for each source IP, which will be a signature of their dynamics. We're going to use that to try to detect if they're malicious. And what we do then is to create these hypergraphs is we take the nodes as the image path, which is the executable files, and then the destination ports as the hyperedges. So what this hypergraph formation tells us is with who are they communicating with and with what executable files. So it really tells us malicious activity, it turns out, really shows up nicely in this hypergraph formation. And then using this sequence of hypergraphs, since we got it from it's a temporal sequence, right? Since we did these windows of data, 10-minute windows, so there's a timestamp associated with each of it, which allows us then to apply our zigzag persistence pipeline. So the first example here is on one of the host 201, and this is for a malicious source IP. And what you see during malicious activity, or what we tend to see for this specific zigzag persistence in this hypergraph formation, is that we get H1 during, so what's highlighted in red is during malicious activity. We tend to get some H1 during malicious activity. Also, the dynamics slightly change during malicious activity. We get these short-lived H0 or D0 here, bars. So you can see during that highlighted area, we tend to get more of these short-lived H0s and a couple H1s. Well, it's not strictly the case. This is what we did. This is the general trends we found here. This was our initial observations applying this method to this data. And then another example of this is an attack on host 501 from another source IP. And again, we saw this trend that the H1 strictly occurred during the attack. And there were, again, these quick burst dynamics during and shown in H0. Some of the future work that we're working on this is with actually applying an autoencoder, because this is very, user specific. A user has to go in and look at these barcodes to try to detect malicious activity. So we can train an autoencoder then instead to be able to detect this malicious activity and pick out these signatures in the zigzag persistence barcodes. So one last thing is how to compute zigzag persistence, in case any of you are interested. It's quite, the packages out there aren't great yet. So the one I used here is called Dionysus, and it works all right. It's just quite difficult to use on a Windows computer, but you can use WSL to run it on your computer. That's my workaround. An alternative, which is relatively new, is a basic applied topology subprograms, another Python library, or BATS. And then all the visualizations here, I used Hypernetwork X for constructing the hypergraphs. So yeah, I want to first, some of the related work, of course, there's this paper, which is topological analysis of temporal hypergraphs. There's also that subsequent paper, which is malicious cyber activity detection using zigzag persistence, which will be coming out soon, where we apply the autoencoder for this detection. But thank you all for listening.